Welcome, everyone. We're delighted to have you with us for another Shout online conference. We have a great day planned for you, and we hope that many of you will be able to join us throughout the day. But if today's the only session you can attend, we're thrilled to have you here, and it's a great session to start the day. By the way, my name is Jonathan, and I'll be on hand throughout the day to help get your questions posed and answered and shared with not only our speakers, but our colleagues joining us from around the world. And we do hope you'll jump in and even start by introducing yourselves. Many of you are doing that in the left-hand area of the screen. And if you're not familiar with the interface we're in, let me just point out where that is. There's an area on the left that's a chat box, and you can type in there, and then we'll go ahead and share your messages with everyone joining us from today. So it's nice to see everyone's introductions. It was also nice to see people introducing themselves in the online community area as well for the conference. And so thanks for taking some time to look through and get to know other people with a common interest. I'm joining you from New York, which might explain the sirens going on behind me today, but as you can see, we've got people from across Europe, Asia, North America. I think I even saw some of our friends from Africa logged in with us today, so thank you. Today's agenda, by the way, as you know, we're going to be talking first about North American forests and what we can learn from the past to protect the forest's future, and I know you're going to enjoy it. We're then going to turn our attention to tigers and what will help save them from extinction. And then we'll talk more, we'll go south into the tropics, south of where I am at least, maybe north of where some of you are, and talk about how plants and animals and people are impacting tropical biodiversity. And finally, twice today, we're doing tree banding updates on our amazing Smithsonian Citizen Science Project. We're going to hear from some of the folks who are doing measurements, and if you're not involved in the project, it's not too late to get involved. So come to one of those 2 sessions. You can check back on the program page for those times in your time zone. And by the way, I would like to thank the partners that make the Shout project possible. In addition to the Smithsonian, whose experts you'll be hearing from during the course of today, we are also joined by Microsoft Partners in Learning and teachers who are joining us from throughout the Partners in Learning network, and also taking it global. And you'll be hearing about some of the work you can do in the global classroom after each session, and we hope you'll stay tuned for that. Thanks to all the partners. I think that's about it for me. I do want to mention one last thing. We're closed captioning today's session, and that's we hope you find that a useful service. You'll see those captions below Jonathan's slides. If for any reason you need to turn those off during the course of the event, you can do so. Feel free to use the little CC button, and you can use the display menu to turn those off. I keep thinking of one more thing, so maybe this is the last one more thing, so hang in with me for another moment. If you are following us on Twitter today, we'd love to keep track of what you're up to and maybe be part of the conversation there. So use the hashtag #ShoutLearning so we can see what kinds of takeaways and things you're sharing. And don't hesitate to invite your colleagues and others to join us. It's never too late to pop in and be part of the conference. As you know, they're free and open to anyone. And we're also on Facebook, and we'll be sharing updates there as well, and hope you will too at facebook.com/shoutlearning. And when we're done with today's session, we're going to have a wonderful drawing captured by our friends in London. Chris Wilson from Scarberia is online with us today, and he's illustrating our session, and we'll be posting that graphic like we have with all of the others from the prior conferences. Here's a few, including one on forests and deer that you might recognize, and here's one on documenting our landscape. So we'll look for a drawing like this from Chris in the days following the event today. Now, I'm ready to go ahead and thank you for your indulgence and for joining us today. And I'm going to go ahead now and introduce Jonathan Thompson. He is our first speaker, as you know, and he's going to be talking about North American forests. Can we learn from the past to protect their future? Jonathan's a forest landscape ecologist at the Smithsonian's Conservation Biology Institute in Front Royal, Virginia, and he's a research associate at Harvard Forest, which is a 3,000-acre long-term ecological research site in Massachusetts. And I know that Jonathan spends a lot of time looking at data and studying the forests, and today he's going to share with us some of his work and what he's up to and some of the things that he's thinking about, and maybe we should be thinking about too. So Jonathan, thanks for joining us.
Thank you, Jonathan. I'm very excited to be here. I want to thank both Adam and Jonathan for helping set this up. I do spend most of my time either in the woods or alone in my office looking at data. And so this is a really exciting opportunity to get to share some of the work I do with people from all over the world. It's amazing to see the list of people who've joined us and the geographic scope. Today, I'm going to talk about North American forests. As Jonathan said, I'm a landscape ecologist, and I don't know if many of you have heard that term before, but what that means is rather than study individual trees or a couple trees or a single stand of forest, I tend to think about forests at really large spatial scales, so thousands of square kilometers at a minimum, and I tend to think about them over very long time spans. So today we're going to talk about northeastern U.S. forests, their past, present, and future. So if we put those in context, we can see here we have a map of the contiguous 48 states in the U.S. I'm sitting in Northern Virginia, but most of my work is up in the northeastern corner of the U.S. here. While about 30% of this region is forested, about in the northeast, that top corner that I just highlighted there, in that region, if we zoom in, we can see all that green area is northern hardwood forest. And so in that, what I'll be referring to is the northeastern forest. In that region, it's over 70% is currently forested. You can see along the coast is where a lot of our major cities are, and a lot of the people who live in the United States live right here in that corridor. It's some of the most population-dense part of the United States. So to me, it's pretty interesting that we could have both such an epicenter of human population and have such high concentration of forests. We sometimes joke that there are trees in the overstory and people in the understory in this landscape. To understand these forests, we have to go back in time because they've really gone through a tremendous amount of change, maybe unlike anywhere else in the world, at least this eastern North America. And so what I want to do first is move back to the pre-settlement forest and start to think about what this area looked like before Europeans settled North America. At this time, there was a population of Native Americans, but that population was fairly small, particularly compared to the human population now. And so at the time, the forests were considered old-growth forests. The trees were very large, and they continued clear across the region, except when maybe a hurricane or small clearings for Native American settlements. But generally, the area was considered to be 95% or more forested region. So we're going to walk through a couple of these pictures. You see this one is old growth. This is actually a diorama that has been built out of wire and clay and paint, and they exist at the Harvard Forest up in Massachusetts. And so these are pictures of those dioramas, and they're going to walk us through the land use history real quick so that we can sort of move from this pre-settlement period up to the modern landscape, just so we understand the history of the forest and how it's changed through land use. So this is before European settlement. At about the time of 1650, people moved in throughout that northeast region. The population of Europeans was still fairly low, but they started to clear the forest. And they would clear it both by burning it and cutting it down, and they were making way for settlements. These were people sort of escaping Europe and trying to make a new life in North America, and so they would create their farms. And at this point, they were largely subsistence farms, which means they were just growing enough to feed their families and maybe take a little to market. Over time, through the next 100 years or so, most of the land in Northeast was cleared. So while it's all forest now, there was a period in about 1800 that nearly as much as 75% of the landscape was cleared. At about the time of 1850, there was what we call the period of agricultural abandonment, and people started leaving their farms. And so I wonder, could we bring up a question we have? Why do you think farmers in New England started abandoning their farms in the late 1800s? And I think, Jonathan, they can just go ahead and click on their screen. Is that right?
That's right. You can review the choices. We've got A, B, C, and D. And then go ahead and just click the circle next to the one that you think would answer that question. And in a moment, Jonathan, I'll go ahead and share the results and we can see what people think. I'm going to go ahead and do that now. We've got a little over 50% of people with their votes in, so let's see where it stands. More than half, a vast majority actually, are saying it's all of the above. Would they be right?
That is exactly right. And so at this period, at about 1850, is when the human population started really growing, and there were urban centers throughout the Northeast, and so people started moving to the cities. They were able to move to the cities because what is essentially the answer C there, because the Erie Canal was built and there were other forms of transportation that allowed food to be moved into the cities. You no longer had to grow your own food in order to live, and so the economies were changing. There was becoming more of an urbanized society, and the farms in the Midwest, moving west of New England, had fewer rocks and had more fertile soils. And so they became more of the breadbasket for the cities, which started to dominate the East there. And so that's a great job. 68% of you saw that one as D, all of the above. So in New England and throughout most of eastern North America, the land wants to be in forests. So I don't know how many of you live in that region, but if I were to stop mowing my lawn and if I just waited about 10 years, I would start to have a forest again. And that's exactly what happened. We had what's called the process of succession starts, where different species of trees move in over time. And so starting at about the late 1800s into the 1900s, we see this trend of increasing forest cover. And with it, we have the return of wildlife and all the things we associate with forests. By the time, throughout the 20th century, from 1920 to 2000, that was really the trend, just reforestation, until you move up into today's landscape, which is mostly a young forest by tree standards. Most of the trees in the Northeast are, 80 to 100 years old, and they represent this legacy. So these forests are quite a lot different than the historical forest. You can see in this picture here this old stone wall. And if you walk anywhere through the forests of New England and the Northeast, you'll find yourself stepping over the remnants of old stone walls. And that is evidence of this land use history that we've just walked through with these pictures. You'll also see barbed wire through the trees. And if you look at the soils, you can see many of the soils have been plowed. And that's evidence of what they grew there. And so historical ecologists are able to piece together the history of every piece of land by looking around for evidence like stone walls and tilled soils. So I'm very interested in how I'm sorry, I wasn't expecting this slide just yet. So here's a nice graph, and each one of these lines represents one of the northeastern states. And you can see in graphical form what we just walked through in pictures, and this steady decrease of forest cover. And so you can see on this is the y-axis over here, and we can see more and more forests being lost till about 1850. And this is about the time that Thoreau wrote Walden, if you're familiar with that book. And so you think of that as, back in the pristine New England. Well, actually, it was at the height of deforestation and the height of agriculture in New England. And then on this axis, this is the human population. And so this is a little counterintuitive that you'd expect more and more people, and coincident with more and more people, you see more and more forests as you move up. What do you think is happening here from a time about 1990 to 2010? And we have another one of these questions up. You can see that the trajectory of forests are changing.
And by the way, as people think about what might have been happening around that period, I just wanted to point out that as you were showing some of those images, especially the modern forest, in particular the modern forest, we had a number of people who started to recognize that as their backyard or areas that they know from having grown up, and that in addition to stone walls, cellar holes are some of the things that people identified. So your images have resonated with some. And
it's a real part of the landscape. This is even the most wild sections of the northeastern landscape are, it was probably a farm just 150 years ago. Even if they just used it for grazing and not actually growing things, really most of the trees, as much as 70% of the trees, were cut down.
The results are showing that people are choosing C as the winning choice here.
Yeah, well, they are good at this, aren't they? That's exactly right. And to me, it's a pretty startling transition. You can see in each one of these states, we've started to see a decline in the past, several decades. And so we don't have a pop-up box for this, but maybe people can just chime in on the chat there. So we had this one deforestation around from 1650 to 1850. And then now we're starting to see another trend of deforestation. What's different about this modern deforestation as opposed to the post-European settlement deforestation? Does anybody just go ahead and write in some of your ideas, if you would?
So yeah, go ahead and use the chat box. What's different from the deforestation that we see, that first dip, versus that newer one? And feel free to use the chat on the left.
So now we identified the right answers. Forests are now being cut down for houses and cities. So how's that different, right?
Stanley's saying that in the current situation, the current deforestation, there's more concrete and pavement involved. A thought echoed by Janice as well. That there's a loss of open space is something that Cindy in Shelter Island is sharing. In this case, Molly is saying that the land isn't being used for agricultural purposes as it was in the post-European deforestation.
Yeah, so that's right. I mean, I think of this modern deforestation as a hard deforestation, and that first deforestation is a soft deforestation for exactly that reason that I said before, where if you stop mowing your lawn or if you stop plowing the land, it wants to come back to forests, and we were able to get this sort of second chance to get our forests back and our landscape back and all the benefits that come with them. That's not quite as true when you lay down a layer of asphalt over the ground and build cities up. It's hard for me to imagine anyway that we could have this sort of second chance again. So in my personal beliefs are that we need to do what we can to conserve the existing forest, because we've been given a second chance and it's not likely to happen again. And so we'll talk later in this presentation about the trends towards deforestation. But for a moment, I want to talk about what are some of the ways that the modern forests, now that we do have forested landscape again, that they might be different from pre-European settlement forests. And if you want to chime in some thoughts there, we can take... So we have a new question now.
Yeah, there's the question. So, what are some of the ways the modern forests might be different from pre-European settlement forests? Um, Stephanie, hi Stephanie, good to see you, of course, says that maybe there are more invasive species. Amy in Seattle says younger trees, and Abby adds less biodiversity. A number of people saying that younger trees.
Right. That's exactly right.
Smaller trees, different kinds, more of the same kind of trees from Catherine. Mike says they're less able to fight off insects. Fewer successions, says Hillary, so they're different species. More damage done by man-made buildings, Natasha in Washington adds.
Right. Well, many of you brought up the fact that we could have different tree species there, and so that's a good answer. There were a lot of good answers there, and they're definitely younger. That's for sure. We moved from sort of old growth forests where most of the trees were, hundreds of years old, till now the average age of a forest in New England is, less than 70 years. So one of the things I'm interested in is about the change in species composition from the pre-European forest to the modern forest. But that's a tricky question to have to answer because there weren't ecologists running around in pre-European days thinking about biodiversity and thinking about species distributions and how forests respond to different gradients of climate and things like that. And so we've had to be pretty kind of creative about how we can recreate the historical communities, the species composition. And one way that I'm very involved in is using what are called witness trees. And what a witness tree is so when they were settling the region in the Northeast, they were setting up towns and properties, and the early surveyors of the time would mark off usually either 2 square mile or 6 square mile blocks that were going to become properties that they would encourage settlement and agriculture. At that point, they were still forests, and they would use trees to mark the corners of the property. And the surveyors would write down that it was a 12-inch oak tree on the northeast corner, or a 15-inch maple tree, for example. And sometimes they would physically mark the tree themselves. And you can see in the top right corner of this slide, that's an example of where a surveyor had carved in the property number, the identifying marker there. And you can see on the left is young George Washington. He's the first president of the United States. You probably have heard of him somewhere along the line. But before he was a general and before he was even in the Army, he was a surveyor. And he collected a lot of witness tree data, and we have his old records that say a lot of things about the property, but what I'm interested in is anytime he wrote down the name, the size and species of a tree and where it was located, we write that down. And then we can start to recreate the historical tree composition, which is kind of an accidental use for those surveyor notes. I'm sure George Washington wasn't thinking of an ecologist in the year 2011 using his notes to recreate the biodiversity of the landscape, but that's exactly what we're doing. So with a colleague, we've had to go to the old town records in each one of the towns in the Northeast and these old dusty manuscripts, and we've gone and collected 1,275 town surveyor records that include the mention of over 350,000 trees. And so what that map shows is the distribution of those towns that we've been able to collect tree data from. So we're going to look at a bunch of maps, and we're going to talk about the tree species that were in those towns back before they cut them down for agriculture. So it's our estimate, it's our best estimate that we have about what trees existed at that time. And then we'll compare that to modern data that the Forest Service, the U.S. government, has collected in recent years. So we're going to see a lot of maps like this.
Before we go on, one quick question I wanted to touch on a third grade class joining us from Ms. Jones, Washington, D.C. classroom wants to know, can we reestablish tree species that may not be around anymore?
Well, it depends, and we'll talk in the next few slides. We're going to go through a handful of species that have seen changes in one direction or another. And if you don't mind, I'll just click one slide ahead because it's a good example of just what the class is asking about. We have the American chestnut, and here you can see on the left, these dots represent the every town that had any chestnuts recorded in their witness tree records. And on the right, we have every town that has any records, except in the right, you don't see any dots at all. And that's because there are no more American chestnuts in New England. And the reason for that is a fungus that was introduced in the year 1900. And that fungus came from China, and it affects chestnut trees and it kills them before they reach an age at which they're able to produce seeds. And so chestnut went from being a dominant tree, particularly south of Pennsylvania, south of where my maps extend. Chestnut was they say 25% of the trees in the forest were chestnuts, and now zero trees are chestnut, at least adult trees. And so your question was, can we reintroduce the chestnut or any tree? In this case, the chestnut, we can't because the fungus is still in the air and in the soil. And so what scientists have done, now that fungus that kills American chestnuts, it comes from Asia. In Asia, where it's a native fungus, a native mushroom, they have Asian chestnuts there that are resistant to that fungus because they evolved together. And so what we've started doing is hybridizing American chestnuts with the Asian chestnuts. So now we have Asian chestnuts that are American chestnuts that have 1/16 Asian genes in them, and that actually makes them resistant to this fungus. And so now we have, this is pretty new science, and so now the challenge is, how do we get these little trees that we're growing in greenhouses out into the landscape? We need sort of a Johnny Appleseed model, somebody to go around and plant all these things in the forest. And so that's an example where, American chestnuts were gone as of 1940. And so for the past 70 years, there's been no American chestnuts. And now geneticists and botanists have created this hybrid chestnut that they're trying to reintroduce into the forest. And so that's a pretty unique example. In large part, most of the tree species that were around in pre-European are still around at some level. And so the chestnut is sort of this stark example.
One quick follow-up question here. In terms of, this one's from Katie, is there any way to stop the fungi from growing or spreading?
Well, I don't know the specific answer, but it totally spread throughout the East in 1900, from 1900 to 1940. And so now it's just there. And so unless you were trying to, spray the whole area with fungicides or something, which would have all sorts of collateral damage and kill off all sorts of mushrooms that we like, there wouldn't be a real way of getting that fungus out of the ecosystem. It's now an invasive species that lives underground in little spores that's really hard. And so really the only hope we see for chestnut is a reintroduction of these hybrid American Asian chestnut breeds. You can see in that slide, those are chestnut trees, and if you look close, it's sort of a fuzzy picture. That's because it's an old picture. And but there are men standing at the bottom of that chestnut. So you get a picture of what a big and beautiful and dominant trees chestnuts were. And, it's sort of, it's sad to think about that this big living old, king of the forest is totally extirpated. So We're going to move on to some other species now. Remember, these gray areas just represent where we have data. They don't say anything about the trees, actually. That just means that we have some data one way or the other. And then the dots represent the population of the trees. And so here's cherry, and here we have an opposite trend. All the dots in here are pretty little, which means the cherry was around before European settlement, but it really wasn't popular. And here we look in modern forests, and the cherry is a pretty abundant species. Does anybody want to take any guess as to why cherries are more abundant now?
It's a good question. This tree has taken a different path than the prior chestnut tree. Why are there more cherries now? Anyone have any ideas? We're starting to get some responses here. Everything from George Washington's help to less competition from other life forms. That they are invasive, asks Stanley.
Well, here we happen to be talking about native prunus trees. There are a lot of invasive trees too, but in this particular example, I'm speaking to native.
They're replanted for cherry farms. Darren says maybe and he also echoes that it's a popular form of lumber. Larger trees are not taking over the land. People like them as ornamental trees.
Oh, these are great answers. It's many things, but maybe the primary thing, and lots of answers have come in. I might have missed it, but cherry is what's called an early successional tree species, and so they come up right at the edges, and they require a lot of light, and so they tend to come up when you abandon a field, or if you have an edge between a lawn and a forest. They like open areas. They're not very long-lived. They tend to, an old cherry would be 80 to 100 years old before they just die of old age, and that's pretty young for a tree. And so, but they come up right away. And so we tend to see more of them now because we have more of these young forests on the landscape, whereas in the pre-European time, it was closed forest. There wasn't a lot of open area, open fields, and so there wasn't a lot of these conditions that cherry really like.
And by the way, for the record, Cindy was among those who did get it as an early succession tree before you said it. So kudos to Cindy and others.
On Shelter Island, New York. Way to go, Cindy. That's right. Exactly right.
By the way, one quick question that did come up. You talked earlier about using those historical records from the surveyors in terms of trying to figure out what forests were like in the past. And Carmen is complimenting you on your interdisciplinary approach using history and talking about biology. In addition to the historical records, are there any other ways that we can find out what forests looked like in the past?
Absolutely. And so one very popular way is to use pollen cores. And if you go to pollen is in the air. The allergy sufferers know that better than most, and pollen lands on lakes, and it will settle to the bottom of lakes, and every year it will lay down a layer of pollen upon layer of pollen, and that's happened over thousands and thousands of years. And so if you take a core from the mud of that lake and bring it up and are very careful, and you slice it, a centimeter by a centimeter, and look at the pollen are distinguishable to species. And then you can reconstruct the vegetation back thousands of years, so way back further than these historical witness tree data. And so that's something I'm actually involved with as well, but it won't be in today's presentation. I think of these two things as very complementary because what's great about pollen data is the temporal span, and that you can go back thousands of years, back to the last ice age, and you can see how climate has affected tree species distribution. The downside of using pollen data is they do represent just one point on the map where you took that core and then went through the pollen. And to analyze a single pollen core, you go out in a boat and you drill that, and it's about 10 feet or about 3 meters or more, and you go through it and you measure all the pollen. It could take years to do that to a single pollen core. So it's much harder to get the spatial distribution, and because pollen flies long distances in the air, it's difficult to say exactly where individual trees start and stop as far as their range boundary. But that's another way that people reconstruct historical vegetation.
Great, thank you.
Yeah. So here's American beech. This, in case you were curious, is my favorite tree species. I don't know if you got to be a forest ecologist to have a favorite tree species, but I do. And we can see that there are a lot less beech now than there were in the pre-settlement time. I don't know how we're doing on time, Jonathan. I would love to, go through each one of these and take people's best estimate as to why the changes. Do we have time to keep doing that?
Yeah, let's go ahead and do it on this one here. I'm going to go ahead and bring up your poll here on the top left of the screen.
Oh, right. The beech was one of our specific ones.
Yeah, there we go.
I got one. So why are there fewer beech trees today?
And we have almost coming up on a third of people responding. Let's go ahead and get it to half here before I show the results so we can be a little bit... All right, I'm going to go ahead and share where we're at. It looks like the majority are saying that it's a slow-growing species and it's still recovering from the agricultural period.
That's right. So beech, that is one of two answers. This was a bit of a trick. We had two answers, and A is also correct in that there's a beech bark disease, which kills young beech trees. But you sort of you got the answers right sort of in proportion to the effect of the problem. The fact that it's a slow-growing species still recovering from the agriculture period is the big reason we see less beech today than in pre-European. But this beech bark disease is increasingly becoming a problem, though its spread is not it's not as widespread as maybe that chestnut blight was. But we're real worried about the future of beech and this beech bark disease. We don't have any kind of quick fix for this, and so we may be looking at the end of beech. The fact that beech is such a slow-growing species, it can live in the shade. It's actually the most shade-tolerant deciduous tree in the world, and so you can put it practically in the dark and it won't die. That's a little exaggeration, but it needs a little sunlight, but it really can hang out in the understory, and it just bides its time. It doesn't grow much while it's there, but it's waiting, and then should a tree fall down in the overstory and make some light available to it, that beech will take off. And so they sit and wait, and that's their strategy. They grow slow, and that's not a great strategy for recovering from widespread agriculture, as it turns out, but evolution didn't really select for widespread agriculture. So beech is one of these species we see a big change in. Okay, we're gonna move on to maple. Now this one is another big change. We see maple has just exploded in the modern forest, and I'll just tell you why that is. And I think when I think of maple, and it's mostly the red maple that we'll refer to as opposed to the sugar maple, both though the witness tree don't distinguish between the two, and so I'm unable to make that distinction when I look at those historical data. But red maple is really what's popular now, and red maple is, to me, like the raccoon of trees. It likes to be in sort of edgy, half-human, half-wild habitats. It grows fast in the sun. It grows in, behind people's houses. It doesn't, its seeds travel real far. It's basically well adapted to living in a human-dominated society. And so maples have really taken over. And we're looking at a future of maple forests for, the indefinite period. Now, oaks are the other one the oaks, I believe this is the last species we'll talk about before we move on to other topics. And you can see here that oaks have declined, particularly in that sort of Connecticut, Massachusetts area. And we see a lot less oak. And I'll tell you what you can't see in this map, but is true, is that there aren't a lot of oaks in the understory, which means that the oaks that are there are dominant, they're in the overstory, but the future of oak is really uncertain. And does anybody want to take we'll take a moment just to think about why we might be losing oak. And I'll tell you, there's probably no wrong answer, because this is a question that is debated fiercely among forest scientists. I see Anne ask what species of oak. Here, because the witness trees didn't differentiate, they would just write down ye old oak or whatever they'd write down in 1750. I have to lump the red oaks and the white oaks and the chestnut oaks all into one. So here, I'm just speaking about the whole genus Quercus. So why is it we think oak wilts? Yeah. Highly valued for lumber. It is true. That is our most valuable lumber species in the area. So that's a good answer. Oak wilt and moss. This is a situation where it's sort of death by 1,000 cuts. You almost can't be wrong. Everything is taken out oaks. One of the problems is deer find it delicious, and they eat oak seedlings, and we now have more deer in this region than have ever been here in the history of North America. There have never been so many deer, and they both like to eat acorns, and they like to eat oak seedlings, and so that's keeping them from coming up. But it's also true that there used to be fire. I see Ann Lewis, and she said fire suppression. That's a good answer, too, because Native Americans used to light fires to open up their hunting grounds, and that stimulates oak regeneration, and that's no longer happening. We don't have a lot of fires. It's a very humid area. And so it's all right. The one last thing I want to say about oak before we move on, and it relates to our discussion about chestnut before. Chestnuts, you've probably seen them, the nuts themselves. They're a big, hard nut, and they have a lot of calories, and they're really important for wildlife. And so when the chestnut disappeared, we had oaks really stepped up with their acorns to sort of fill that niche of providing food for wildlife. And so now oaks are the only what we call hard-mast species, meaning they create hard food. And what's important about that is you can bury it and you can come back to it and have yourself a meal in the wintertime when nothing is around. And so this is called a functional niche, and the chestnut had the functional niche of providing chestnuts to wildlife, and oak stepped up and took that functional niche away from when chestnuts went away. But now that we're losing oaks, there are no other species with hard mass, and that is going to have cascading effects through the ecosystem and affect a lot of wildlife. And so there are a lot of people very, very concerned about the future of oaks, and people are reintroducing fires and planting oaks and trying to make sure there's a future for oaks of all species. Okay, we're going to... Oh, there's eastern hemlock. I forget my own slides. I want to talk about one last species. I apologize. Eastern hemlock is a species that has not changed much between pre-European settlement and modern forest times. But see that picture down in the bottom right? That is Hemlock woolly-adelgid. It's a little aphid-like critter that is now killing off hemlocks. And it is also an invasive species. It is also from Asia. It doesn't affect Asian hemlock, but it affects North American hemlock, so maybe we'll be able to do some hybridization, but as of now, no one's figured out a way to do that. Hemlock used to be an abundant species through the southeast. Smoky Mountain National Park, for example, in Tennessee and North Carolina, used to have about 20% of the area was in hemlock, and today 0 is in hemlock. And that adelgid is marching north. And so I expect that if I come back and give this presentation again in 15 years, there will have no dots in Pennsylvania, New York, and Massachusetts, and it'll just be in the far north as it marches north. And so that's another species we're worried about. So you can see there's a lot of things affecting forests and a lot of things affecting tree species. So now we can see we have a colorful version of that map. And so one way to think about change is one species at a time, and that's what we've done. We've walked through all these different species. The other way is to think of it as all species, and so there's some statistical ways that you can think about multivariate change. And so this is a map of just a way to think of overall change. And what do you see as a pattern there? It's sort of a red meaning more change and blue meaning less change. And so, while there's a lot of variability, you can note that there's a lot of blue up in Maine. And any guess why that is an area that is most similar and hasn't changed much?
We're seeing perhaps as a shift to the southwest, says Wendy.
Yeah, why do you think that is?
Less people,
what is it about the north that has less change? Less development, less people, remote, that's all right. And there wasn't agriculture there. So that history of forests that I gave in the beginning where the whole land went agriculture, it was a little misleading because in the far north of Maine, it was too cold and too mountainous to clear the land. And so what we have is areas that were continually forested from pre-European settlement times till now. And so that's evidence, not that we really needed it, that the change we see in forest composition is a result of the history of land use, and that it takes an understanding of history to have an understanding of modern ecology. Okay, so this is sort of a rhetorical question. Why do we care about forest ecosystems? Well, we know they provide us with wildlife habitat. They provide us with biodiversity and recreational opportunities and all sorts of direct economic benefits. I'm surrounded by paper and wood in my office. Maybe you are too. We can see here's a hunting stand and kayaking, different types of recreation, maple sugar. There's all sorts of reasons. And then there's also an element of forest that is just critical infrastructure for the planet. Forests could well be thought of as the lungs of the planet. They absorb carbon dioxide from the atmosphere and release oxygen, which we breathe. So as services go, we really owe forests a big thank you for the air we breathe. They filters the water, the recreation, and everything. One piece that you'll hear a lot of talk about today, and we only have, about 10 minutes left, and we're going to move on to talk about the role of forests and how they affect climate change. And to understand that, we need just a quick primer on the carbon cycle. And so this little graphic shows that the process of photosynthesis requires light and it requires carbon dioxide. And as trees absorb carbon dioxide, they store carbon. And so you can think of the things that forest carbon cycle as having 4 parts to it. The forests sequester carbon. That's a term you hear a lot with relation to climate change, and that means they take carbon dioxide out of the air and they store it in their wood. They also emit carbon dioxide, and carbon. They do that just through respiration, autotrophic respiration, which is breathing. And they also emit carbon dioxide when they decompose. And so every time a tree falls down, it turns back into carbon dioxide and is left in the atmosphere. Or if they burn, it emits carbon dioxide. And they store carbon as well. A tree is, give or take 1 or 2%, 50% carbon. And so if you put a tree on a scale and weigh it and divide it by 2, you know about the weight of the carbon in that forest, which is just a convenient number. I got to say, for a guy who does a lot of carbon budget calculations, 50%, it couldn't be much easier than that. And they cycle carbon, which is to say they just move carbon around through different parts of the atmosphere, through the soil, and through the foliage. And so understanding that about the carbon cycle, we can see that northeastern forests play a particularly important role, and that is because they're young. And so they are still growing, and they're still storing more and more carbon. And so what this measures is the continual uptake of carbon from 1992 to 2008 using what's called an eddy flux tower at Harvard Forest. It's the longest running tower in North America. And it shows how many tons of carbon per hectare are stored per year. The reason it has a sawtooth structure is because in the wintertime, it doesn't store any carbon because all the trees fall off. And so you can see the seasonal patterns of summer, winter, every one of those sawtooths. And as we grow up, you can see that the overall trend is a storage of carbon. And so it's very important to understand how much carbon gets absorbed by forests. This is all a picture of carbon. We release carbon when we burn fossil fuels. Remember, we call them fossil fuels because they are fossil plants. They are just like forests that have been buried for millions of years, and when they were forests, they stored carbon just like modern forests do. And now when we burn that fossil fuels, it's just like burning up forests and releasing that carbon dioxide in the atmosphere, which is a greenhouse gas, meaning it warms the atmosphere and causes global warming. This graph shows that same history we've been talking about all day, and which is about 1700. This is all carbon released. Here we cut down all the forest as we move towards about 1900, and then the forest started to grow back. And now we can say that up to 20% of our carbon emissions are absorbed by forests. And that's a tremendous service that forests provide. How are we doing on time, Jonathan?
We have about 5 to 7 minutes left.
Okay. So one thing I do, I said I'm very interested in long time frames and over large areas. So I'm interested in this question, will forests continue to reduce carbon pollution into the future? So we talked about the past and we talked about the present. And now real quick, we're going to talk about the ability for forests to sequester carbon in the future. Now, I'm going to focus on Massachusetts for this next part. That's the state that I'm from, and it's also, I work up at Harvard about half-time. I'm half-time at Smithsonian, half-time at Harvard. And so the bit I talk about now will just relate to Massachusetts, okay? And there's nothing on that side. Oh, so a couple of the things that are affecting the answer to that question, will forests continue to sequester carbon? Here's two headlines that I clipped. They were published within a couple days of one another. States like Massachusetts losing 72 acres per day to urbanization. So those are all forests that would have been storing and sequestering carbon, but instead we're going to release all that carbon to the atmosphere, and we're going to remove any ability for them to sequester carbon into the future. That's the bad news. The good news comes below. 11,000 acres are protected in 2007, and that's under conservation easements. And those are the forests that we can count on sequestering carbon into the future. So I'm interested in, simulating using computer models and mapping software to simulate different scenarios of housing development, logging, and conservation, and ask what if these things occur, and what does it mean for forest species and wildlife and carbon sequestration over large areas. And so to do that, I've created a computer model that's actually just thousands of lines of computer code and would be really boring to look at. And so instead, I made this little cartoon bubble, which sort of summarizes what my model does. And it takes the forest condition, and then there are given probabilities associated with whether any given pixel on my landscape is developed, what's the probability that it's harvested, what's the probability that it's conserved, or that it's affected by wind or ice. That model then aggregates up those changes. It grows the species using a model that simulates growth, and then it outputs maps. And then it does that, and then I can change these probabilities and try to learn about the future of forests. And so a lot of my time is spent, unfortunately, inside writing computer code so that we can answer questions about the future. The big player is forest loss to development. What you see, this little gray speckles within the Massachusetts, that's all represents areas that were lost to development between 1985 and 1999. And so in order to determine the probability of future forest loss, I thought, well, I bet future forest loss will resemble past forest loss. And so I asked, in a statistical sense, how forest loss between this period might be related to all these variables you see on the side. Is it related to the time people commute to work? Is it related to the road density? Is it related to home prices? And I used and you see all these variables. I actually looked at about 50 different variables, but I just wanted to give you an example. And down at the bottom is the type of development that we see as it punches holes in the forest. So, and here's a little way that we can answer that question. This is a statistical model made into a decision tree. And so you can walk your way down any of these arrows. So we can start at the top and we can ask ourselves, is an area conserved? If it is conserved, yes, then the probability it'll be developed is 0, and that's what that blue box shows down at the bottom. And then you can walk your way through the other way. Okay, if a pixel is not conserved and its distance to built is less than, in this case, 283 meters, and it's on a slope that's greater than 7.9%, then the probability is 10%. And so we can do that, and in the computer we can run every single pixel, so it's 1.1 million 1 hectare pixels, through this decision tree, and that determines the probability. So all of these probabilities were based on what we saw in the past, and then we just spin that forward to look at the future. And this is what we get. So the top one, we used what decision tree I just showed you for development. And here, red colors are higher probability that areas will be disturbed, and blue colors are low probability that it'll be developed. And on the bottom, it's the same technique, though I didn't show you the decision tree, but for timber harvest. So I think we have a quick question we can bring up. I know we're running low on time, but why do areas with the highest probability of development seem to have the lowest probability of timber harvest? Anybody have any ideas there?
Good question. We've put it up there just below your picture so people can focus on it.
Not a lot of ideas on this one.
Here's a response. People looking for parks in their neighborhoods. What else we got? Let's see. No need to harvest. People want trees for shade.
All right. Well, since we're running short on time, we can. It turns out where people live and where people want their natural resources extracted, they don't want to see it. People don't want to look at the timber harvest, and so areas that people want to build their house don't tend to be the same areas that people want to have their forests harvested. And And for that reason, all the mills tend to be in rural areas. NIMBY, I see a lot of people writing NIMBY, not in my backyard. That's exactly what I'm talking about. People want to separate the two. So it's interesting to see these two maps have such a different pattern as to where the harvest probability is and where the development probability is. I don't need you to look at all these lines, but what these lines represent is the sequestration of carbon over the future 50 years as they are affected by climate change, development, and harvest. And the one thing I'd like you to take away from this is that all those lines trend upward for 50 years. And so that's good news. That, and why we see that is the forests are still recovering from agriculture, so they're still growing. Eventually, growth will level off as growth and decomposition tend to about equal one another. So old growth forests, they do sequester some carbon, but they don't put it away quite as fast as young carbon. And you can think of it a bit like, young trees are going through puberty and they just really going through a growth spurt, and that's what's happening in Northeast right now. The trees are in the prime of their life, and so they're really growing. So under all scenarios, regardless of climate change and development and harvest, we see increases in forest growth. If we look at it at the effect of those impacts, conversion here means conversion to develop uses or development. We can see that if we didn't do anything at all, if we just let them grow, we would have in the next 50 years 70% more carbon in the forest. But if we develop at the rate we're developing, we would have 18% less carbon than we would. So the number would still be positive, be 52% increase. Timber harvests have a much smaller effect on carbon sequestration than development, and that's because you allow the trees to grow once you leave the site. You don't pave it over. And so that has a much slower, even though timber harvest occurs on twice as much area, it has just a fraction of the effect. And climate change, interestingly, has a positive effect on carbon sequestration. And that is because in this section of the world, climate change is going to result in warmer and wetter conditions. And that trees do like warmer and wetter conditions. And so we're going to skip through this. If I had a take-home message, it would be continued forest recovery will be the dominant mechanism driving forest growth over the next 50 years. And that losses due to land use and forest conversion could reduce that by up to 20%. And that's all I have for you today. I'm sorry I got rushed there at the end. I just like talking about this stuff too much.
No, I don't think any of us would argue that you like talking about it too much. I think we're glad you're thinking about it, doing the work you're doing, and taking the time to share it with us. So thank you, first of all. What I'd like to do is just review a couple of quick things, and then I'm going to let our captioners rest and our illustrator. I've put Chris's drawing up on the screen so we can see what he's been up to in terms of capturing his takeaways from our discussion. And then maybe we can just do a quick 1-minute lightning round with a couple of questions. For those of you who need to run, we'll record this last minute or two here, and you can come back and check in on it later. But if you can stay another minute or two, I just want to take a couple of questions that have come in. So, Chris, thank you for this great drawing.
Yeah, look at that.
I did want to point out where people can go ahead and follow up on all of the kinds of issues, the important issues you raised today. First of all, you can continue the dialogue over in several different venues. But first of all, if you're a teacher and you're among us today, don't forget that you can download a teacher's guide and include some challenges that relate to this and the other sessions today. You'll find links to all of these on shoutlearning.org. You can also contribute back through the Partners in Learning Network and the tiged.org/land site. You'll see that Shout link on the screen as well. Don't forget that we've got Facebook and Twitter at hand, and there's also the Taking It Global site I just mentioned is what we call the Shout Global Classroom. That's a great place where you'll see some questions posted for discussion among your students if you're with us as part of a class today. And there's some great student work. We'll also be looking at some student participants and hearing from some teachers during our tree banding updates. So we hope you'll take a look. What great way to be inspired is to look at what some other classrooms are up to. And by the way, we've got some people joining us from a variety of different locations today, including our conversation leaders here from two of our sites in Belfast, and we want to welcome them. So let me go ahead. I'm going to, at this point, remind you that we have another session that begins in an hour, and we're just going to take maybe 2 or 3 more minutes for a few remaining questions that I wanted to see if we could address. So with that, if you're game, Jonathan,
absolutely.
Let's go ahead and take this question. There's a question about hybridization that you mentioned earlier, and does that have any negative impacts, such as does it affect other trees or crowd out other native species? When you were talking about the chestnut, that came up, I think.
Well, it's a good question, and it's always something to be concerned about letting genetic hybrids out and trying to get them into the wild. It's for that reason that they've tried to make as little of the genetics the Asian tree as possible, so it's just 1/16, and it's at this point we don't see any negative effects. We feel that it's very similar to the American chestnut, which we know had a niche in these forests, and so we feel confident that it will be a lot like reintroducing the native species. Having said that, we've been wrong on these things before when we try to reintroduce new things, and sometimes it's smart to have an abundance of caution when you're manipulating Mother Nature, that's for sure.
Here's another lightning round question. You touched on this a little bit. In terms of the quality of the air we breathe and the water we drink, Laura wanted to know how forests affect air and water.
Well, forests create the air, so they split the carbon dioxide, they store the carbon and release the oxygen, and so you need the oxygen. And as far as water goes, forests hold soils in place and transpire water, so they bring water out of the soil and into the air as part of the water cycle, and they filter the water as it moves down into the groundwater and into the streams where we end up drinking it. And so when it comes off the parking lot and it's full of contaminants and whatnot, the forest soils clean out that stuff and before it gets to your faucet.
Okay, and I think the last question we'll take today, and by the way, I've put an evaluation up at the top left of the screen. We'd love your feedback about today's session. So that's our last question for you, would be to please fill out that evaluation. But I think the last question we have is from Catherine. How could kids help plant trees, and how long does it take for them to grow?
It varies tremendously from species to species as far as how fast they grow. Kids have been part of a lot of reforestation campaigns in the West after fires, I can say, and particularly there were a large set of fires throughout the 50s and 60s, and now those trees are large, mature forests, and now these once school kids are walking with their kids and are able to look at the trees and say that they planted them. I think it's a great way to get kids out in the woods and start thinking about it. Trees do grow fairly slowly, and that's what's made me resort to using simulation models, because I'm not patient enough to wait around and see what they'll do.
Well, Jonathan, thank you so much for all of your time today and sharing the good work that you're doing and making it so accessible to all of us. I wanted to remind you, I've just put a link back to the page that you used to access today's session. From there, you can get to the Global Classroom, the teacher community. You can get back to shoutlearning.org and find your way to the teacher guide I mentioned and all of the related resources. We'll be back in just under an hour with our next session on the Global Tiger Initiative, and we hope you'll join me and Marshall and Anna, who will be leading that session. Jonathan, thank you again, everybody. Please fill out the evaluation, and we'll see you all soon. And a special thanks to our captioner and our artist, Chris Wilson, in London for keeping up with us even as we went a couple of minutes over. Thanks again, Jonathan.
Oh, thank you.